Good morning. I hope you all had a wonderful weekend. We're going to continue on talking about types of titrations today. On Friday, we looked at the strong acid plus strong base titrations, and we briefly overviewed a strong base plus strong acid. And now today, we're going to look at the weak acid plus strong base, and then later on we'll talk about weak base plus strong acid. And the equations for here are separated by region. And like we talked about before, the initial point means that none of what you're adding has been added to the solution. So the order of the chemicals makes a big difference. The weak acid is like what we're starting with, and we're slowly adding in a strong base. So initial just means you have just weak acid, all right? There's no strong base. And like all the weak acids in this section, we don't even have to worry about 100 times K less than C. pH equals minus log square root Ka times Ca, or Cwa for the weak acid. In the pre-equivalence region, where the moles of what you start with are greater than what you're adding, so NWA, moles of weak acid, greater than moles strong base, in this region now, it's acting like a buffer. And in this equation right here, this is a type of the Henderson-Hasselbalch equation. Now in Henderson-Hasselbalch, it was pH equals pKa plus log base over acid. And in this kind of titration, all right, you're adding a strong base to a weak acid. So just like the other examples we've seen so far, the moles of weak acid are not changing, all right? That's what you start with, and you're not adding anything else. The moles of strong base, however, will change depending on the volume. So the volume in liters of strong base that you've added times the concentration of your strong base is how you're going to find moles of strong base. And what happens in this region is the strong base will lower your weak acid. So your weak acid concentration, what moles of weak acid will go down. But in the process of lowering the weak acid, the conjugate base is created. And if you add like 1 mole of strong base to 5 moles of weak acid, then you'd have 5 minus 1, you'd have 4 down here. But as much as the strong base lowers the weak acid, it creates more of the conjugate base. And if this went down by 1 mole, that's going to create 1 mole of essentially conjugate base. So mathematically, it works out really cool. pH equals pKa plus log moles of strong base divided by moles of weak acid minus moles of strong base. And again, the moles of weak acid doesn't change. It's the other part that changes. That's why this region in here is pretty flat, all right? We'll talk about this half equivalence thing later too. Now at equivalence, the equation looks kind of funky, but at equivalence, your weak acid has turned into a weak base, and that's the only thing that affects pH. So this equation right here is nothing more than a rewritten 14 plus log square root Kb times Cb. Now Kw equals Ka divided by Kb. So if you want to solve for Kb, then Kw divided by Ka is there. And a lot of times you already have Ka, so instead of having to recalculate explicitly Kb, you can plug it in right here. But it's cool to use Kb there instead if that's easier. And then like before, moles of weak acid haven't changed. You need to divide by the total volume to find that part. But that's essentially then the concentration of your weak base. And then finally at post-equivalence, now the strong base is greater than your weak acid. And this equation looks a lot like post-equivalence between strong acid, strong base, except instead of NWA, you had NSA in those examples, but same thing. It's like leftover moles of strong base divided by total volume. So notice that total volume appears in these two. It doesn't really appear in this one. Buffers are kind of independent of volume, which is weird. You always know NWA right away, the moles of weak acid. That's part of the initial part. You're just trying to see the effect of the strong base as we go through. One last thing. At equivalence with strong acid, strong base, and strong base, strong acid, the pH was just equal to 7. But because the conjugate base of the weak acid is the active player at equivalence, your pH will be basic. It'll be greater than 7. So So if you have a titration graph and you're trying to figure out if you're titrating a weak acid or a strong acid, if you're titrating a strong acid, this equivalence point, the steep part of the curve, that would be equal to 7 or pretty close. But at this level, then pH is greater than 7, you're going to have a weak acid. The conjugate base is present. Any questions before we look at an example? All right. Benzoic acid is a very common weak acid, just like acetic acid. Probably the second most common weak acid is benzoic acid. And benzoic acid is a benzene ring, C6H6, but one of the hydrogens has been replaced by essentially a carboxylic acid. And Chem 222, we talked about how carboxylic acid has a C double bond OOH. But anyway, benzoic acid, like all the weak acids, has a weak conjugate base. It's called the benzoate ion. And you can see it's this hydrogen here that's been removed. There's a negative right here. It's resonance stabilized, but that's fun from Chem 222 that we don't need to worry about here. But anyway, in this problem, you're starting with a benzoic acid solution, a 0.025 moles per liter, and you have 100 milliliters of it. If you stop right there and turn milliliters to liters and multiply by moles per liter, that's going to tell you NWA, that moles of weak acid. And that number, like I said, won't change in all of this problem, all right? So I stopped right after there. I would find the moles right away, NWA, not the band, unfortunately. Anyway, but I won't go there. 0.1 liters times 0.025 moles per liter will give you the moles. That'll be a constant. Now we're adding in sodium hydroxide, a strong base. We're trying to find the pH of the initial solution, i.e. what it is before you've added any sodium hydroxide. And finally, if you have a weak acid or a weak base, you're going to have to find K somehow. So in this case, Ka 6.3 times 10 to the minus 5. I'm going to abbreviate benzoic acid as HBZ and benzoate as BZ minus, but this is the full formula. Questions on this part? Okay. So initially, pH for any weak acid minus log square root Ka times Ca or Cwa, either way. So you have everything you need to do this. Ka, that number, Cwa or Ca, 0.025, minus log of all that action, 2.90. Check yourself. It's a weak acid, so your pH that you calculate should be less than 7. If you had a pH of like 8.9, something's probably not quite right there because greater pHs larger than 7 would be basic. Questions? Now, it might be also nice to know what the pH is after some random number of milliliters of base have been added, all right? So this point, we're definitely no longer at initial point, but now we don't know really if this is pre-equivalence, equivalence, or post-equivalence. So when you get to a point like this, you've got to start comparing the moles, all right? If the moles of benzoic acid are greater than sodium hydroxide, then you're pre-equivalence. If they're equal, you're equivalent, stuff like that. So again, the thing to remember is you've got to think about the moles, compare the moles, all right? So we already talked about finding NWA, the moles of weak acid. You take the volume in liters of the benzoic acid, 0.1 liters, and you multiply by the concentration, i.e. moles per liter of the weak acid. So liters times moles per liter give you moles. There's 0.0025 moles of your weak acid. If the sodium hydroxide moles was equal to this, that's what equivalence is. But when you do this kind of problem with the concentration of NaOH and the volume that we've added so far, you can see we're 0.0010. So the moles of strong base are less than the moles of your weak acid. That's what pre-equivalence is all about. The moles that you're adding are less than the moles that you started with. So for this region, we want to use that pre-equivalence thing, that kind of Henderson-Hasselbalch looking expression. In this region, the sodium hydroxide annihilates the weak acid, all right, 100% product favor. And in the process of knocking the benzoic acid out, you make benzoate, the conjugate base of benzoic acid. So in this pre-equivalence region, the buffer kind of ideas will apply, all right? Because you're gonna have weak acid left over and this amount of conjugate base. So that's why we're kind of using these buffer-like expressions and stuff here. But mathematically, it's pretty chill. You need the moles for these regions. pH equals pKa plus log moles of strong base divided by moles of weak acid minus moles of strong base. Now pKa is minus log of Ka, so minus log 6.3 10 to the minus 5 comes out to be that. That's the number that's going to go right here. And then here, moles of strong base divided by moles of weak acid minus moles of strong base. And again, if your calculator starts giving you weird expressions like undefined or something like that, it probably means you have a log of 0 or something like that. That just means you're not using the right equation for the types of moles you have. But here, you shouldn't end up with that. When I plugged this in, I had a value of 4.02. Any questions? Okay. Now, it might also be interesting to know what the pH of other points is, and 12.5 milliliters is what this question's all about. So we're gonna have to figure out moles and all that kind of jazz. From before, the moles of weak acid again, they're not changing, all right? So that number you're gonna use multiple times. The pKa might be helpful too, which we did on the last screen. So when you figure out the 12.5 milliliters, how many moles that is, it's this number. And again, this number is less than moles of weak acid, so NWA larger than NSB, pre-equivalence. We're back to this equation right here. But the reason I bring this up is because now at this point, moles of strong base, 0.00125, and we're dividing by 0.0025 minus 0.00125. And mathematically, this works out to be a log of 1. And in the logarithm world, the log of 1 is equal to 0. So at this point, pH and pKa are equal to each other. And this point right here is the so-called half equivalence point. And if you have an acid which has never been studied before, and you know it's weak and stuff, and you want to find the Ka, the half equivalence point is really, really handy, because at that point, pH and pKa are the same. And you could turn your pH at that point into a Ka to calculate what it is. So when you're doing a weak acid plus strong base, a lot of the graphs will show a half equivalence point, all right? And half equivalence is kind of cool for chemists because at that point, all of this stuff goes to 0 and pH and pKa are the same. So it's a quick way to tell that your calculations are right. If you know Ka, you can turn it into pKa. Your pH should be the same. On the other hand, if you have an unknown acid, you can find the Ka. If this was the pH, that equals pKa at this point, you could turn that into a Ka by going 10 raised to the power of minus pKa. Any questions? All right. This is the half equivalence point, and the moles of the strong base are equal to half the moles of the weak acid, or the moles of what you're adding are half of what you started with. At this point, pH and pKa are the same, which is really cool. And if you want, you can then find Ka. You could also go on and find Kb. Kw equals Ka times Kb, et cetera, et cetera. Another useful point about this is that the volume to reach equivalence, all right, half of that number is going to be the volume to get to half equivalence. So one way that we've talked about on Friday is we took the moles of what we started with and we divided by the concentration of what you're adding to find out volume. That's the volume to reach equivalence. Half equivalence literally is also half the volume to equivalence. So if you knew that the volume was 25 milliliters to reach equivalence, half of that number would be the half equivalence volume. So there's different ways to kind of play this and stuff and figure it out. All right, at equivalence, we'd like to figure out the pH, and at that point, we no longer have any benzoic acid because the benzoic acid, our weak acid, and the sodium hydroxide are in equal mole concentrations. And sodium hydroxide, a strong base, pushes to the opposite side, so we're going to have just benzoate left. But benzoate is a weak base, all right? Weak acids have conjugate bases which are weak and vice versa, acids to bases. So benzoate itself is going to be a small producer of hydroxide. So we're trying to figure out how much hydroxide is there and what the pH will be. Now, if hydroxide's being created, do you think the pH will be larger than 7 or greater than 7 at this point? Greater, that's right. If hydroxide is high concentration, or at least some, it's going to make hydroxide times hydronium. It's going to make a basic pH. That's what hydroxide is for. And basic pHs should be greater than 7. So at this point, at equivalence, your benzoic acid and sodium hydroxide equal moles. All right, they're wiping each other out in my juvenile way of talking about things. You end up making sodium ions, which are pH boring. They don't have any pH effect. Benzoate, which is the conjugate base of the weak acid, and that will make hydroxide. And water, which is pH of 7. So what we're going to do now is focus on that benzoate ion. And again, benzoate is a base. pH should be basic. pH should be greater than 7. The effect you're seeing is not from the sodium hydroxide at this point. It's from the benzoate, the weak acid of the benzoic acid. Okay, so we need the moles of benzoic acid, all right? We need the moles of sodium hydroxide. And like we did earlier, volume of the weak acid times concentration of the weak acid, and remember to put your volumes in liters, this many moles of benzoic acid. And again, at this point, that's equal to the moles of what you're adding, the sodium hydroxide. So at equivalence, we have this many moles of sodium hydroxide. 0.1 mole per liter is the sodium hydroxide concentration. That's going to allow us to solve for the volume of strong base. So in this case, 0.025 liters, that's the volume of sodium hydroxide required to get to this point. So from here, it's just plug and chug, woohoo! And Kw, 10 to the minus 14th, all right, the only K I'd like you to know. You divide by Ka, which is another given. This gives you Kb. Over on this side, the moles of weak acid at this point have turned completely into moles of conjugate base. So this number is the same as the moles of conjugate base at this point. And in the bottom, you just want to divide by the total volume, all right? So we had 100 milliliters of the benzoic acid. That's where the 0.1 comes in. And the sodium hydroxide here is going to be 0.025. So you can see it's like Kb times Cb, and the Cb is moles over volume. Moles of the weak acid are all moles of weak base at this point. Divide by total volume. pH should come out to be greater than 7, should come out to be basic. 8.25. Woohoo. Questions? Cool. Now, it might be nice to know what the pH is going to be after equivalence though too. And you can do it for any point in this kind of thing with this kind of stuff, which is cool. So let's say that we wanted to know what the pH was after 1 more milliliter of sodium hydroxide had been added. So it took 25 milliliters to reach equivalence. 26 milliliters would be just 1 more milliliter, about 20 drops. And to do this, we'll still need that moles of weak acid, all right, the total moles and stuff that are present. So from before, 0.0025. And you also will need the moles of strong base. So molarity times volume in liters, it's like moles per liter times liters, 0.0026. And again, you can see now that moles of strong base are larger than moles of weak acid. So this is what post-equivalence means. More of what you've added than moles of what you started with. So 14 plus log leftover moles of base divided by total volume is what you want to use here. And again, this top part here should be a non-zero, non-negative number. It should be positive. It's going to be small, but that's okay. We'll divide by the total volume. In this case, from the strong base, 0.026 liters. Still have the same 100 milliliters or 0.1 liters in the denominator. Your pH should be basic, 10.9. Any questions? So if you've done these kind of problems right, remember that the pH will constantly be either increasing or decreasing. In this case, since we started with an acid, the pH should start acidic, and we're adding a base, so the pH should constantly be increasing, getting larger. So at this point, your initial pH at 0 milliliters of sodium hydroxide started at 2.9 or so. Then at 10 milliliters, we had a 4.02, all right, which is right about there. We did the 12.5 milliliters, the so-called half equivalence point. At that point, it was a little bit more basic, 4.2. What is this pH equal to? pKa, good, that's right. The half equivalence point, half equivalence volume leads to the pH, which is equal to pKa. So 4.2 then is an important number for scientists because it'll either equal pKa if you're given Ka, or you can find Ka, 10 to the minus 4.2 would give you Ka. Then at equivalence point, your pH should be basic. And again, note the volumes here. Half equivalence times 2 gives you equivalence. Also, equivalence divided by 2 gives you half equivalence. So that's another way to kind of check yourself on this. Visually, the equivalence point will be the steepest point, and there's fancier math ways to do it, but for us, that's fine. So you can kind of see, okay, right in the middle there, that would be the equivalence point. And again, half that value should be half equivalence. And then finally, just a little bit extra, your pH jumps pretty good. So in this case, it jumped to 10.9 at 26 milliliters. So again, this point would be equivalence, this point would be initial, and anything between there, pre-equivalence, and anything after it, post-equivalence. And bam, you can solve for the pH of any acid-base combination. Well, weak acid plus weak bases are lame. You don't have to worry about that. They're not very effective. But these guys, oh yeah. Anyway, 99.9% of all titrations, it's something with a strong acid or a strong base. So that's why we're not looking at weak acids plus weak bases. I'm getting too excited here, I know. It's a Monday. Anyway, questions on... All right. The strength of your weak acid really makes a big difference in terms of what the titration looks like. And one of your examples in the titration calculations, the graph looks quite different from the other ones. And that's because the strength of the acid or the strength of the base makes a pretty big difference. A strong acid, strong base has a very steep, kind of like S-curve right there, very easy to see. But notice here what happens is the Ka gets weaker, all right? As the Ka gets smaller going up, then the acid is getting weaker, all right? When you get up to like 10 to the minus 10, whoa, it doesn't hardly look at all like it, like it's just a little bit and stuff. Here's a 10 to the minus 8th and stuff. So a lot of times the shape of what the S-curve looks like will make a big difference. And several of you have asked about the one graph, which looks a little weird. Yeah, it's supposed to. Your K is pretty weak, so it's not going to look like a standard one. A lot of times in examples, you'll have like something, one of these kind of Kas, or maybe even the yellow one, but the weaker they get, the less obvious the S-curve is, and that's very, very normal, all right? You don't have the pump that the stronger ones have. Another thing we haven't talked about too much, but I want to just very briefly talk about, something we'll actually do in lab this week, is we're going to look at a polyprotic acid. Now, poly means many, many proton acids. So this means that these acids give off more than one H+. And a classic example, and something that we'll look at very similar, this is phosphorus acid. We will look at phosphoric acid, very similar. But anyway, look at this graph. It shows the first two equivalence points. So there's like one on top of each other. And this is what happens a lot of times with a polyprotic acid. Now, to interpret this, all right, every time you have a steep part right here, that's going to be one of the equivalence points. So right here is the equivalence point between H3PO3, phosphorus acid, and H2PO3-, the conjugate base of phosphorus acid. So in this graph, 50 milliliters would be the equivalence point. Now, like we talked about earlier, the half equivalence point is pretty important for scientists, and you can do it either by looking at the moles or the volume. So if it took 50 milliliters to reach equivalence, half equivalence would be the half equivalence point. So 25 milliliters, the half equivalence volume, will lead you to a pH which is equal to pKa. And that's the pKa of your first acid proton. But if you have more than one acidic, and there's several of these kind that exist, you'll actually usually see a second equivalence point. So this second steep part right here, this is now the equivalence point between H2PO3-, which is a weak acid as well, and its conjugate base, the hydrogen phosphite ion. So in this case now, the equivalence point right here, all right, this is between H2PO3- and HPO2-. Sounds like a test. Anyway, if you wanted to find Ka2, the second acid equivalence point, halfway between the two equivalence points. So if the first equivalence was at 50, the second one should be twice that number, or 100. So at 75 milliliters, that would be your new half equivalence point for the second acid. And if you go over at that point, that pH should equal pKa2. It's kind of a handy thing. In lab today, or thanks for playing, this week, all right, we're going to actually titrate phosphoric acid, which is really similar. You should be able to see the first two. The third one is so weak, I don't think you'll be able to see it. But from the first two, then, you can predict what the pKa1 and pKa2 will be by finding those equivalence points. It's kind of an interesting thing. Now, mostly what we're focusing on in Chem 223 are the monoprotic acids and the monobasic systems. So a single S curve. But if you do have a multiple one, you can totally do it. Sulfuric acid would have two of these and stuff. You could count, you could figure out. Any questions? This is also a way that if you have a brand new acid, and they're discovering acids all the time, if you had an unknown acid and you didn't know anything about it, you could slowly titrate in a strong base, all right? And if you see more than one equivalence point, then that's a good sign that you have a polyprotic acid. So it's just a visual way that you can quickly see what's happening. Cool.
When an antacid tablet containing sodium bicarbonate is dropped into water, a reaction occurs that produces hydroxide ions and carbonic acid. The carbonic acid decomposes to form water and carbon dioxide gas, visible as bubbles. The hydroxide ions react with acid in the stomach to produce water.
The last kind of titration that we're looking at is when you have a weak base plus strong acid. So if you had like ammonia, or if you had any of the amines and stuff like that, they would be really good weak bases. And there's similarities between these kind of titrations and the weak acid strong base we just looked at. The difference, of course, being that because you're starting with a base, weak or strong, your pH should be basic, all right? And as you add an acid, and a strong acid at that, your pHs should consistently, in this case, be getting smaller, all right? The acids make the pHs get smaller, the bases make the pHs get larger. Just like before, there's essentially four important parts: the initial region, the pre-equivalence, the equivalence, and the post-equivalence region. And all of these are based on moles. So the initial point, you would have only moles of weak base. You wouldn't have any moles of strong acid. The pre-equivalence means you have more moles of weak base than you have strong acid moles. Equivalence is when they're both equal. And post-equivalence now means that the strong acid is dominating the weak base. A couple of things about these. Your equivalence point here will be where these two are equal. So the weak base moles and your strong acid moles are equal. They annihilate each other. So no more of either of those left. However, the weak base produces conjugate acid. Acid being the operative term, your equivalence point should be acidic. It should be less than 7. So if you see an equivalence point that's less than 7, that means you probably started with a weak base. The other thing is that at the quote-unquote half equivalence point, you're still going to have pH equals pKa. Now, because you're starting with a base, it may be more interesting to you to find Kb, but you can do that. pKa plus pKb equals 14. You could find pKb, and then 10 to the minus pKb would give you the Kb value. You could also turn pKa to Ka, and then Kw divided by Ka would give you Kb. But just realize that pH and pKa are the same. You have to translate your pKa to the other one. This region in here, once again, is kind of like a buffer because you have now a weak base, and as the strong acid is added in, you create some of the conjugate acid. And so it'll act like that. That's why we're going to use the Henderson-Hasselbalch-like thing. And again, at that half equivalence point, your pH should be equal to pKa. And you can translate the pKa to Ka and then Kb if you want, or pKa to pKb, then to Kb. Oh boy. So anyway, let's say that you have a weak base and strong acid titration, and you're going to equivalence. How are the moles of the weak base and the strong acid related when you're at equivalence? The same, that's right, they're equal to each other. So if the moles are equal, which is what equivalence means, you don't really have any weak base or strong acids. Strong acids and strong bases push to the opposite side. So you don't have any strong acid, you don't have any weak base, you're going to create water, but what does the weak base create? Conjugate acid, a weak acid, that's right. And acid being the operative term, your pH should be acidic. It should be less than 7, all right? It doesn't care, don't worry about the concentration. It's really not equal to 7 because the conjugate plays a factor. It won't be greater than 7 now because that weak base has turned into a weak acid. And it may not be, like 6.999 or something, but it will be acidic because of that weak acid part there. Any questions on that? So the equations for these, some of them look similar and some of them are new, but they're all kind of the same idea. Initially, you have only the weak base, all right? So 14 plus log square root Kb times Cb, or Cwb since it's a weak base. That's what you want to use for the initial point. The pre-equivalence looks very similar to the pre-equivalence weak acid strong base. We're using essentially here a Henderson-Hasselbalch, so pH equals pKa plus log leftover moles of base divided by moles of strong acid. Now, if you're given Kb, you have to turn that into pKa. So Kw divided by Kb would give you Ka, and then minus log of that would give you pKa. There's a couple different ways to do it, but that's what I would do. Henderson-Hasselbalch is always base over acid. So you're figuring out like the leftover moles of weak base on top, and you're dividing them by essentially how many moles of strong acid have been created. Now remember that NWB here, the moles of weak base, not changing the whole time on these problems. So this is a constant. NSA will be the volume in liters times the concentration of the strong acid you added. So these parts will change as you go through the titration. At equivalence, you have a weak conjugate acid present, and all the weak acids, pH equals minus log square root Ka times Ca. Now Ka is also equal to Kw divided by Kb, but if you have Ka from up here, plug it in, takes care of both of those terms. Oh yeah. Getting too excited here. Anyway, moles of weak base, like I said earlier, that's a number that's not going to change in these whole titrations. So if you had that from up here, you're still going to have the same number here. The volume of the weak base will not change, so that will be a constant, but the volume of the strong acid needs to be applied. Remember that this isn't really moles of weak base, it's just numerically equal to the moles of weak base. At this point, all the weak base and the strong acid have knocked each other out, but however many moles those were, that's going to equal the moles of your conjugate acid, which is really what we're trying to figure out here. And again, at this point, your pH should be less than 7, right? Because you have a weak acid present. And then finally, the last part, the strong acid is dominating. So minus log leftover moles of strong acid divided by total volume. And remember, all these total volume terms are liters. So NSA, moles of strong acid, minus moles of weak base should be a positive number. Calculator will give you an error. And you divide by the liters present. This is the same as the post-equivalence equation where we had strong base plus strong acid. It's just that instead of NWB here, they said NSB. And it was also the pre-equivalence equation for strong acid plus strong base. In that case, again, instead of NWB, it said NSB. These equations kind of repeat each other, and that's what I'm hoping you're starting to see. It's not that you have to do 4 titration types times 4 equations, 16 equations. No, no, no. Several of them repeat. They're very similar to each other. Look for those patterns. It makes your life a lot easier, you know. Any questions? If you have a nice pH meter set up, the data that comes out of a pH meter, either that you hold manually write down or like we'll do on a computer, will tell you like where titrations are and stuff like that. However, sometimes it's nice to visually know that you're past the titration point. And an indicator is kind of a cool thing and stuff like that to focus on. An indicator is nothing more than usually a transition metal acting as a complex ion, and it turns color in the certain range of pH values. So for example, one indicator is called methyl violet, and you can see that at super acidic pHs, like 0 and stuff, it's yellow, but when you get to about a pH of 1 or so, it goes violet. So if you had a titration where the equivalence point was about 0.5, which is incredibly acidic, but anyway, then methyl violet would be a cool indicator to use. Because if you started at a pH of 0, which is possible, super concentrated things, it would be yellow, and then you add just a little bit of base, it should start going violet. So indicators are great color things to let you know and stuff that you're turning into a different pH range. Now, most of the time, all right, things like phenolphthalein, which is one I've used a lot right here. You don't have to pronounce it or spell it, by the way, because it's got all those weird pH things in it. But anyway, phenolphthalein is a very common indicator because it turns from colorless to red right about pH 8 or so, all right? So a lot of these things will be colorless while they're acidic, and as you get to basic pHs, they'll go red. So for example, if you have a strong acid plus strong base titration, what is the equivalence point pH for those? 7, nice job. So strong acids, strong bases, and strong base, strong acids, pH should be 7 at equivalence. So phenolphthalein is a pretty good indicator because if you're going from an acid to a base, i.e. strong acid plus strong base, colorless, 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 7 is where equivalence happens, and it just takes a little bit to make the pH skyrocket. So if you start seeing a red, or what I would consider more pink, honestly, color change, that means you've gone from acid to base. That means you've gone through equivalence. So it's a cool way to kind of visually know that you're past equivalence. Now you have to pick the right indicator for the right transition you have. So for example, let's say that someone was mean to me and they put I can't even say it, that green thing, B green. I'm not an English major. Anyway, let's say they added B green instead, all right, the solution would be yellow, 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 and then right about a pH of 4 or so, it would turn from yellow to blue, and I might think, oh cool, my reaction's done. No, it's not, because it turned blue way too fast. You have to have an indicator that's going to be around the change of your equivalence point, all right? Because otherwise, you'll start seeing these beautiful colors, and I'm totally distracted by color. However, it won't be very helpful. You're not actually at the equivalence point. So I bring this out because having a color change, it's kind of a good thing, all right? Like there's one thing intellectually to know all the moles of this and moles of that, but it's also nice to see, oh, my color changed, the reaction's done. As long as you set the reaction up with the right color change, you're good to go. But if you don't have the right one stuff, you might be weird. In the next slide, I'm going to focus on this bromothiamyl blue. That's this one right here. And you can see that yellow is usually like pH of 5 or so, and blue maybe 6, 7, something like that. So here's a picture I found online of different pH ranges, and these are all the same compound in there. It's the bromothiamyl blue compound. And so you can see that at pHs usually less than 6, it's kind of a yellow color. At more basic pHs, it's more of a blue color. And then in between, you've got some kind of weird blue and yellow, greenish, kind of nasty looking. But anyway, showing you're in a transition. So the color itself will sometimes give you a hint like what's going on. A lot of these are nothing more than weak acids and their conjugate bases as well. And so one form, weak acid or conjugate base, will be like yellow, and the other form will be blue. It's its own very weak system, and the color change happens because of the conjugates, which is kind of cool. Here's a question you could see and stuff like that. Which indicator do you want to use for this titration? Do you want to use phenolphthalein or methyl red? All right. So first of all, let's look at this graph, all right? It goes blue, it's the red one right there, or it's the blue one right here. All right, if this is the equivalence point, all right, and the equivalence point here, 5.5-ish, something like that, we're starting with a base, we're going to an acid. Is this a strong base plus strong acid, or do you think it's a weak base plus strong acid? Good, Anthony. Weak base plus strong acid. If this is the equivalence point right here, all right, then this pH is acidic. And acidic equivalence points only happens when you have a weak base plus strong acid. Those pHs will be less than 7. What's the approximate pH if you have a strong base plus strong acid? 7, that's right. So visually you can tell here and stuff that this is probably a weak base plus strong acid. Now, ideally, you would like the color change to occur right around the equivalence point. And this pink up here shows that basically phenolphthalein at pHs higher than 8, it looks kind of pinkish, purplish, reddish. I don't know, I don't know what I'm wearing basically. But anyway, under those pHs, it's clear, all right? So let's say that we were titrating, pink, 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 it goes clear. Have we gotten to equivalence if you were just using the colors? No, right on. You haven't gone far enough. And the fear of the analytical chemist, the chemist concerned about moles per liter and stuff like that, is that you won't go far enough. And so in theory, you could stop here before you got to equivalence and your stuff would be toast. A better indicator to use here would be this methyl red, because it looks like it's yellowish kind of until around here it goes red, all right? So the indicator color is closer to the equivalence point than phenolphthalein will be. So in this case, your pH less than 7 at equivalence, all right? And that equivalence point is where you ideally would like your color change to occur. So in this case, methyl red is right in this zone right here. That would be a better pick. Phenolphthalein works a lot of times, especially when you have acids and you titrate with bases. But really in this one, the methyl red would be a better choice. There are thousands of indicators out there. All right, in the days before technology, people had all kinds of different indicators for different titrations. And it was really nice. Then as technology started to be introduced, they wanted to make sure that the technology was telling them correctly. Now with the technology that people have, I mean, electronics are awesome and you can see the graph come out, steep sides and stuff, but even then, even now, I still find the color change kind of reassuring, all right? Like, you know that it's, you know, your technology is calibrated right and stuff like that. And so indicators still have a function besides just being cool to look at. Questions on any of this? Okay. So that's really the end of this section. Some things that might help, all right, this Buffers and Henderson-Hasselbalch guide will really help with all of the pre-equivalence regions with weak acid, strong base, and weak base, strong acid. And it will also help, of course, with buffers, which is a big part. Concept guides, again, are gonna have worked problems to go through, so you kind of see like what they are, check yourself to make sure you're happening. The titration guide is going to be really handy. The problem set this week is a little weird at first, but if you think about it as types of titrations, I think you'll get through it pretty well. And then there's types of equilibrium constants, all that jazz. On the side, we'll see some different kinds of buffers today. They a lot of times come in these little colored bottles, and they sometimes will allow you to tell that your pH meter is kind of cool. Any questions on that? Okay, I think I'm going to cut it a little bit early today just because we'll start the review then on Wednesday. So we'll talk more about all that stuff then. Have a wonderful day. I'll see you.